let's continue the lecture. We're going to talk about the chain rule today. So suppose you have a function which is differentiable. Let z equals to f of x and y be a differentiable function. I'm going to introduce a new variable like t such that x and y, both of them are dependent on that new variable, independent variable like t. You can assume t to be, for example, time or any other variable. Suppose x and y are functions that depend on a third variable like t. We can write it this way. We can say that, hey, let x be a function of t and y as your variable defined as h of t. So we have two variables. These two variables are also functions of a new variable like t. Then the question says, so how do we take the derivative of function f with respect to this new variable t? So this is the question that we're going to answer. What is the derivative of function f with respect to this new variable? That's how we define the chain rule. You can say that, well, I want to substitute these two functions for f, then start taking the derivative. Of course, why not? One approach is to substitute x and y into f, and you get a function like this. You get function z, f of your x is g of t. So we just substitute that here. Your y is h of t. Then we take the derivative with respect to t. That's one of the approaches that we have. Next approach is as follows. We say that the derivative of z with respect to t is defined as, well, z is a function of two variables, x and y. In this case, you can write it this way. First of all, you have to take the derivative of x, then you have to take the derivative of y. You can say that, hey, I have partial derivative of f with respect to x times the partial derivative of x with respect to this new variable t. Now we move on to take the derivative with respect to y plus the partial derivative of f with respect to y times the partial derivative of y with respect to t. Note that you can cancel out the partial derivative of x and you get partial derivative of f with respect to t plus the partial derivative of f with respect to t. These two approaches, both of them are equivalent to each other. Suppose you have this function. Suppose f of x and y is defined as x squared plus 2y. Okay, and I say, hey, my function x is sine of t, and my variable y is a function of t like cosine t. That's how I define this function in two variables, x and y, and somehow I try to connect x with t, y with t. One approach is to take the derivative, is to just substitute these two back into function f and get rid of these two variables, x and y. Here you get f of sine t, comma, cosine t. I'm just substituting these two back, which is sine squared plus 2 times cosine t. It means that I have function f defined as sine squared t plus 2 cosine t. Now just take the derivative of your function with respect to t. 2 sine t cosine t minus 2 sine t. This is the first approach. Just substitute that, take the derivative. Or you can apply the chain rule. The chain rule says, okay, the derivative of this function with respect to t is defined as, you get the exact same answer. dz over dt, or the derivative with respect to t, partial derivative of f with respect to x. So the derivative of f with respect to x is 2 times x. Times. Now you have to take the derivative of x with respect to t. The derivative of x with respect to t is cosine t. Plus the derivative of f with respect to y, which gives me just 2, times the derivative of y with respect to t, which is minus sine t. So note that here you have 2x, but what is x? X is sine t. So this is equal to 2 sine t cosine t minus 2 sine t. As you can see, I have the exact same derivative for this function with respect to this new variable. So let us make it more interesting by adding another independent variable like s. So let me write down the summary here for you. If f of x and y, function z, is differentiable, and x is g of t and y is h of t, then the derivative of f with respect to t is defined as the partial derivative of f with respect to x times partial derivative of x with respect to t plus partial derivative of f with respect to y times partial derivative of y with respect to t. Now we are making this a little bit more interesting. So again, you have a function in two variables and it's a differentiable function. Suppose x and y are functions that depend on two variables, s and t. So we are adding two new variables. Suppose one of them is time, the other one is, for example, temperature or the location. So suppose x is defined as g of s and t, and y is defined as h of s and t. Now we can define the partial derivatives of function f with respect to s with respect to t. Again, one approach is to just substitute these two back into the function and take the derivative. So one approach to substitute x and y into z and take the derivative. Second approach is to use the chain rule. Again, the outcomes must be the same. So the chain rule says the partial derivative of function z with respect to x, with respect to s, not x, is equal to, here you have the partial derivative of z with respect to x times partial derivative of x with respect to, so x depends on s and t, and we are taking the partial derivative with respect to s plus partial derivative of z with respect to y. Remember that your y also depend on s times partial derivative of y with respect to s. So the first partial derivative of function with respect to s, now we move on to variable t. We say that, hey, the partial derivative of z with respect to t is partial derivative of z with respect to x, and x depends on t as well, so we have to take the partial derivative of x with respect to t plus partial derivative of z with respect to y, and now taking the partial derivative of y with respect to t. If f of x and y is equal to z is differentiable and x is g of s and t, y is defined as h of s and t, then the partial derivative of f with respect to s is partial derivative of f with respect to x times partial derivative of x with respect to s plus partial derivative of f with respect to y times partial derivative of y with respect to s, and then partial derivative of f with respect to t is partial derivative of f with respect to x times partial derivative of x with respect to t plus partial derivative of f with respect to y times partial derivative of y with respect to t. Let's go over one example to feel more comfortable about using the chain rule. So this example says, we are still on page 1. Suppose you have function defined this way. Let f of x, y, and z be xy plus z, and then x is defined as s squared, your y is s times t, and z depends on t, which is t squared. Let us find the partial derivative of f with respect to s and partial derivative of f with respect to t. So one approach is to just do the substitution. Wherever you see x, write down s squared. Wherever you see y, write down st. And wherever you see z, just write down t squared. So my f, which now just depends on s and t, is equal to x times y, I get s squared times st plus z, which is t squared. As you can see, I changed these variables. I transformed my function from 3 variables into a function in just 2 variables. So I have f of s and t, which is s cubed t plus t squared. Now you can easily take the derivative, partial derivatives of this function. So partial derivative of f with respect to s is equal to 3s squared t, and this guy doesn't have any s in it, so it's going to be 0. You get 3s squared times t. Partial derivative of f with respect to t is equal to, so here I'm taking the derivative of this function. Let's just write it here. Box it here. This is simplified. So the partial derivative of s cubed t with respect to t is s cubed. Partial derivative of t squared is 2t. This is your first approach, just substitution. The second approach is using the chain rule. So I'm just following these 2 formulas. The partial derivative of f with respect to s is equal to the partial derivative of f with respect to x, which is just y, times the partial derivative of x with respect to s, which is 2s, plus the partial derivative of f with respect to y, which is x, times the partial derivative of y with respect to s, which is t, plus the partial derivative of f with respect to z, which is 1, times the partial derivative of z with respect to s, which is 0. Okay, here you have 2s times y plus x times t. What do we have here? We have to do the substitution. What is our y? Y is st, so we're going to substitute that here. St times 2s plus, what was our x? X is s squared times t, and this is just 0. So we get 2t times s, let me see, 2 s squared t plus s squared t, which is 3 s squared t. The same. Now let us take the partial derivative of f with respect to t. Very well. First, we take the partial derivative of f with respect to x. This is just y, times the partial derivative of now x with respect to t. It doesn't have any t in it, so you get a 0 plus partial derivative of f with respect to y, which is x, times partial derivative of y with respect to t, which is s, plus partial derivative of f with respect to z, which is equal to just 1, times partial derivative of z with respect to t, which is 2t. Let's see what do we have here. This is just 0. What is our x? X is equal to s squared. So I get s squared times s plus 2t. I get s cubed plus 2t. As you can see, I have the exact same result by using substitution or using the chain rule. have z equals to x squared y plus 3x y to the fourth. And question says, suppose x is defined as sine 2t and your y is defined as cosine t. And question says, find the derivative of z with respect to t when t is equal to 0. Again, we're going to solve this using two approaches that we have. The first approach, which is substitution. Wherever you see x, write down sine 2t. Wherever you see y, write down cosine t. Just substitute that. So z is equal to sine squared 2t times cosine t plus 3 times sine 2t times cosine t to the fourth. Now we start taking the derivative with respect to t. So remember that here you have the product of two functions. You have to apply product rule. dz dt is equal to. So first we take the derivative of sine squared 2t, which is 2 sine 2t. This is 2 minus 1, so we subtract 1. Then using chain rule, that's what you learned in elementary calculus, times 2, and the derivative of sine is cosine 2t. So this is just the derivative of sine squared 2t, and we multiply it by cosine t. Plus, now we take the derivative of cosine t and multiply it by sine squared 2t. So copy down sine squared 2t times the derivative of cosine is minus sine t. Now we move on to the next multiplication. Product between sine 2t and cosine to the fourth. So plus. The derivative of 3 sine 2t is 3 times 2 cosine 2t times cosine to the fourth t plus 3 sine 2t times the derivative of cosine to the fourth. So you get 4 times cosine to the third, and times the derivative of cosine is minus sine t. Let's try to simplify. This is equal to 2 times 2, which is 4, sine 2t cosine 2t times cosine t minus sine squared 2t sine t plus 6 cosine 2t cosine to the fourth t, and here you get minus 12. So let me write this guy down here for you, minus 12 sine 2t times sine t times cosine to the third. This is the derivative of this function with respect to t. Now we're going to apply chain rule to see that we get the exact same outcome. Can we simplify this more? Sine 2t, I don't think so. Okay. So let's write down the second approach here using the chain rule. dz dt is dz dx times dx, they're using the partial ones, dx dt plus dz dy times dy dt. So the partial derivative of z with respect to x, you get 2xy plus 3y to the fourth times the derivative of x with respect to t, which is 2 cosine 2t, plus the derivative of z with respect to y gives you x squared plus 12x y to the third, and the derivative of y with respect to t is minus sine t. Okay, now we have to substitute everything that here back. So here you get 2 times x times y sine 2t cosine t. So 2 sine 2t cosine t plus 3 times y to the fourth cosine to the fourth of t. Let's close the parentheses, times 2 cosine 2t. So plus 3 cosine to the fourth, 2 cosine 2t plus x squared, which is sine squared 2t plus 12 sine 2t, y to the third, cosine to the third of t. And here we close up the parentheses times minus sine t. Here, if I factor out, let's see, 2 cosine t here, and 2 cosine t, and then if I factor out minus sine t from here and here, I get the exact same outcome. These two are equal to each other. Question says, what if t is equal to 0? If I plug in 0, when t is equal to 0, this is going to be 0. This is 0. I get 6, and here you have 0. So the derivative dz dt yt is equal to 0 is just 6. The same here. If I plug in 0 here, if t is equal to 0, the derivative of z with respect to t at t equal to 0 is equal to. So this is going to be 0. Then I have 3 times 1, 2 times 1 gives me 6. And this is 0, this is 0, and this is 0. So the outcome is equal to 6. The derivative of the function with respect to t, the rate of change of the function with respect to t at time, for example, time t equal to 0 is just positive 6. So next topic is implicit differentiation. Let's get back to elementary calculus, what we learned before. Recall. In elementary calculus, you learned that, for example, if I have a function y equals to x squared, I can take the derivative of this function by taking the derivative of x squared with respect to x, which was 2x. Sometimes you have more complicated function defining this way. X squared plus y squared equals to 2. If they say take the derivative of the function, you can use implicit differentiation. and you have 2x dx, taking the derivative with respect to x, plus 2y dy, the derivative with respect to y, equals to the derivative of constant is equal to 0. Now remember that you divide up everything by dx to write y prime 2x plus 2y dy over dx was equal to 0, and then you say, hey, dy over dx is equal to minus 2x divided by 2y, or negative x over y. We call this guy the implicit differentiation of the function. We're going to just extend the idea and the